seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadow
Okay, good evening everyone. Oh, I see this just isn't going to work. Maybe now. Let me know if you can hear me, because I'm actually not checking if you can hear me. Yeah, you should be able to hear me though. So, good evening and welcome everyone to another of my live streams. Today's moderator is going to be KrzaQ. His nickname is right here. Yeah, here. So, if you have any questions at any time for me, then you have to actually ping KrzaQ on, well, whatever chat you are at. If you are on YouTube chat, if you are on our IRC, or if you are on our Discord chat, because KrzaQ is actually the person who will pass the questions to me using magical methods. Now, today's topic is going to be, it's one of the topics where I'm trying to figure out how something works, and I think I have all the background knowledge required, but I've never done it in the past. So if you prefer topics where I just know what I'm doing, then this isn't one of them. Just go to something else. Otherwise, feel free to suffer with me. The topic is going to be SROP, or Sigreturn-oriented programming. It's basically a variation of, I would call it like, it's not even a variation of return-oriented programming. I would call it, it's like part of return-oriented programming, the same way the magic gadget is. So it's an optimization for return-oriented programming, which is basically using a gadget which has a sigreturn syscall in a specific way, which should ease up exploitation or allow exploitation of some cases. So we'll get back to that in a second, and for now, if you have any questions, again, do ping KrzaQ, and I will go through the usual round of, well, I guess, news / things I usually say, right? So let's check if the desktop is actually selected correctly. Okay, perfect. Let me see. I had a browser. Yes, this is KrzaQ's website. Okay, what happened to my keyboard? Why is my keyboard not working again? It was working before the stream and now it fails, which means I have to apologize, but there are some technical problems which I have to attend to. I thankfully have scripts written to fix everything, so hopefully everything will fix itself in a second. Come on. Oh. Yeah, my keyboard is kind of acting up, and as you remember, like last week or 2 weeks ago when we had the last live stream, I had the same problems, and I do have a set of macro keys, some of which I use to actually zoom the screen during the live stream, so it's quite important that that actually works. And I think last time I had to manually unplug my keyboard, so I have to do it again. Be right back. Okay, let's see if it works now. Okay, it even detected my keyboard, and yes, it works. Perfect. I apologize for that. I don't know, it's like I start streaming and then my keyboard hangs, like the drivers from my keyboard, which is pretty weird. Anyway, this is KrzaQ's website. Again, he's my moderator today, so KrzaQ, thank you for helping me out. And if you have any questions at any time, do ping KrzaQ and feel free to visit his website. Now, as far as usual stuff goes, you might have seen on my blog that I've posted about some call for papers and some conferences. It's usually like the organizers ping me, or I actually co-organize a given conference. So here they are. One conference which is going to take place in May is how do you read it? I think ZivCon or something like that. Anyway, it's a conference basically where red team and blue team like meet, as in actually it's a conference about purple teaming, as in cooperation between red teams and blue teams. And it's happening in Gdynia, it's in English, so do take a look, and there's some discount code if you're interested. Then there are some CFPs which are opened. First is for OWASP Day Poland. This is for, you know, open web security, basically, web application security project, and they have a small-ish, well, not really small, conference in Poland called Poland of Us Day, and they are looking for papers, well, basically, for folks who will come with a lecture and give it. And then there is the Security Pwning Conference, which I co-organize, and there is a CFP to the end of April. So if you're interested in attending, it's in November in Poland, in Warsaw, then attending with a paper or with a lecture, then do submit your paper to the CFP. You can find this on my blog, by the way, it's the newest entry. And yes, and let's move to the next topic, which is the Paged Out magazine, which, as you might remember, is the thing I'm currently playing with a lot, especially if you're on our chat on Discord then, or in IRC, then you might get links or from me about it, or like some random pieces of information. Long story short, it's an experimental magazine where one article is exactly one page, and it's about stuff like hacking, security, retro computers, modern computers, electronics, demo scene, amateur radio, like whatever is deeply technical and is somewhat related to, basically silicone and electronics, then you can basically write about that. And we already have, we have already 9 articles in total which were submitted. We have 3 which were already reviewed, and 6 more are in the process of being reviewed. So that's going pretty well. If you're wondering how an article looks like, for example, this is one from KrzaQ. So it's basically one article, one page. You can actually squeeze quite a lot of information on one page, so even though it seems it might not be enough, based on the articles which are already submitted, that is enough to describe not everything, right? You cannot squeeze a book into it, but for some tricks or some interesting pieces of information, that totally works, and works surprisingly well. So I'm really looking forward to completing the first issue. And if you would like to submit, then go to this page, which I am going to give you a link to. And there are like 5 easy steps, which are totally not easy, about how to write an article, what are the technical requirements, what are the example topics. For example, there are some templates as well, more templates to come, hopefully. If you want to make a template for us for like LaTeX or some other editor, then we totally would be grateful for making more templates. Because the layout is actually something the Forma has to do. Some example topics, just to give you an idea of my vision of what Paged Out magazine is supposed to be. And then there's the technical details of how to write the article, how much space do you actually have, what does it mean, a page, and so on and so on. The surprising thing, which I did not expect at the beginning, would be fonts. Fonts and actually font licensing, because since the authors are actually responsible for doing the layout, they are also responsible for selecting the fonts. And not all fonts can be used for commercial publications without buying a license for a given font. So we would prefer folks to use a font which is on a free license for commercial uses. And that also means that, I have to dig quite a lot through the internet to double check, is this font can I actually use it? We already had a case where one font was free, and but it turned out that you cannot use it for commercial purposes. So yeah, I didn't expect I would have to dig through licenses of fonts, but yeah, I do, and also the other reviewers do. So there's that. And if you're following me on Twitter, by the way, when we get to around 50 articles, we will start to finalize the issue. So this is basically somewhat of a deadline for submission. In all honesty, we'll probably still try to squeeze into the final magazine 75 or ish articles, depending on how many were submitted. So yeah, and it's actually going quite well. I didn't expect so many articles to be submitted so early in the project. So I think we will get enough articles actually to publish a magazine on time, which is in June. If you follow me on Twitter, I actually posted this, which is the final design for the cover art. I did show you the cover art itself previously, but now it's like has, you know, this, I think it's called Bridge, which is on the side of the magazine. This is for a printed version, right? But it will be included also in the electronic version, and yeah, if you want to print it, just print it. And yeah, like this was added with, you know, the number of the issue, the logo of the project, some nice decorations here, and this is the backside. There will be some text on the backside. I am still figuring out what exactly. It will probably be the like supporters and donations, basically, for the issues, because this is a free project. The magazine will be for free, which means there are a lot of folks who are helping out, and one way or the other, and we would like to credit them somewhere. So probably the backside will be that place. Cool. So I think I talked about this enough. Let's go to today's topic, which is, yeah, it basically begins with this paper, Framing Signals a Return to Portable Shellcode, by Eric Bosman and Herbert Boss. And it's a new paper. It's from 2014, if I'm not mistaken. It's actually 16 pages, and it's both about like the SROP technique and how to use it for exploitation, and like how to use it on like 32 bits, 64 bits, and also about it being a weird machine, which means you can actually like just use this one, I think it was just this one gadget to do like loops and to do comparisons and whatever else is required in a Turing complete machine, basically. So I fully encourage you to read the paper. And that being said, I did not read the paper because I prefer to figure things on my own. I did read, however, part of entry on Wikipedia and the manual for Sigreturn, which we will get to soon. The entry on Wikipedia is actually quite verbose, which is quite nice, so I'm going to give you a link to this as well on both chats. And yeah, and also the manual, which might or might not be useful. I guess the funny thing is, like, where was it? Yeah, notes in the manual, it should never be called directly, like Sigreturn should never be called directly. Guess what we are going to do today? Yeah, we're going to call it directly. So this should be fun. Now, let's start with explaining the idea behind it. So the idea is actually quite simple. The Sigreturn syscall is basically one of the syscalls, right? The functions which the kernel gives the programmers to use. It has a simple function. It's supposed to read the context, like, you know, the registers like flags and some other stuff from the stack. So this would be on stack, and like load it into the actual CPU, like actual thread information. So you have like this information, like the state of the registers, the flags, and so on, and you call this syscall, and you have it on stack, and you call this syscall, and it just loads all the register values to the proper places in the CPU. So like if you have in the structure like RAX register value, then it loads it in the RAX register. If you have like ESP or RSP, actually, then you load it into RSP register, and so on. So it basically just loads the context of a thread, and this is useful, and actually this is used because signal handling. So signal handling works kind of like interrupts. It's always a kind of complicated thing for operating systems. So you have your code, right? And your code is executing, like the CPU is executing your code, and it goes like this. And suddenly, like if we would be talking, you know, OS development, an interrupt comes, like some data is ready on some device. So usually that means that you want to stop execution at some point and execute the interrupt handler, which then, like for example, gets the data from the device, puts it somewhere, marks that hey, this data needs to be processed, and gets back to here. Now, the way this is done on this level is basically that the CPU stores some context for the interrupt. Usually that depends on the CPU architecture, but it usually saves the context, being the register state, being some flag register states, and so on the stack of this process, right? And then when it returns, it basically loads the context back so it can continue executing the code. It needs to store the register state, because otherwise, if it would return, then the state would be, totally in the bad shape for the code couldn't continue execution because the register values would be just incorrect, right? Not what it would expect there to be. Now, actually, signal handling on Linux works in a pretty similar way, as in the code executes and suddenly you have a signal, right? And the signal causes a signal handling routine to be executed. And then, and that also means that the state of the code has to be saved on the stack, for example. And when you exit from the signal handler, you actually have to read back the context and go back to executing the code. Now, the read back the context is actually what the Sigreturn syscall is going to do. So the first thing we are going to do today is basically look at that, I guess, just to take a look how it actually works. And then we are going to try to use this in exploitation. I will probably write some really simple, buffer overflow thingy, which we will then try to abuse this method to, to basically do a return-oriented, actually like Sigreturn-oriented exploit. Cool. So let's start with doing this example and basically looking at the debugger, how this works. So I'm going to create a test.c file, and there isn't going to be too much stuff here, just include okay, and I now need some signal handlers, but for that I need man. I don't know if you saw my tweet. I guess I'm going to show you my tweet. It's a bike shedding tweet, but yeah, here we go. Yeah, like this is what I decided is happening. But when I had like 5 years of coding experience, which for me meant I was like 11 or 12 or something, right? I basically just wrote code, but when I like gained experience in time, when I wanted to write a line of code, I started to like reading the documentation on the function I want to use, checking some side cases or edge cases which I expected to happen, and so on, and reversing the function even in some cases. So this is why I'm opening the man now, because I want to check how exactly should I use, signal in this case. So I think it's called signal, or is it called sighandle? No, it's called signal, yeah. So basically this is the function which registers with the kernel. I think with the kernel, I'm not sure. It probably registers it with the kernel as signal handler. So you basically give it a signal and you give it a function, and the function is called when the signal comes to this process. Signals are something which exist in Unix like kind of systems, right? So Linux, for example, or like Ubuntu, Debian, or whatever, right? They do not exist on Windows. Windows doesn't have signals. Windows uses different mechanics to do the same things, which is basically, it's some kind of a small inter-process communication on one side, and on the other side is basically like controlling the processes, like for example, if you want to terminate them early. So that means we need to include signal.h. Perfect. And now we need to do a function, and the function has to have this prototype. So it's void my handler, and then int which, what does it take? It probably gets like the signal that's signal. What does the sig handler get? No. Yeah, signals are fun, by the way. Yeah, it doesn't say. It's probably gets the signal number. We'll get it. Going to check this. So let's call it num, and let's just say we want to printf my handler, and we'll call it with num. It might be quite funny actually calling printf from inside the signal handler, because you know the main application might be in the middle of printf, and actually then and the printf might have some lock, and it might cause a deadlock. So there are all kind of funny situations in signal handling. So signal handling should be done with care, actually, with quite a lot of care. And I think even El Kamtav long time ago had a paper called just let's look for signals. Yeah, delivering signals for fun and profit, where he writes about all the funny stuff with signals. And it's a pretty old paper from 2001, but it's still worth checking it out today. Anyway, I'm not going to talk about that today because that's not really important for today's topic. So I'm going to register this handler. So signal, and first I need the number, and I need the number. The numbers are actually in the 7th page of the manual for signal, and I want it for sighub, because what sighub is, I think, is officially hang up detected whatever, but actually it's used to signal applications that they should reload the config. So if you send a sighub to Apache, it will reload the config, if you obviously have the right permissions to request that. So I'm going to do that and my handler, and now I'm going to send the signal, and sending a signal to a given process is obviously done by the send signal API. No, it's not. It's done by kill API for some reason. So it's probably page 2. Yeah, here we go. So types. So I registered the handle, and now I'm just going to this is going to sound weird. I'm going to kill myself. As in, the process is going to send a signal to itself using the kill API. Programming language is sometimes strange. What's the deal with this killing and children starving because no data is available? Yeah, programming language is really strange. We should not talk around normal people. We might get misunderstood. Anyway. Okay, so first the PID, then the signal. So the signal is 1, but I need a PID. So on Windows you could usually do -1, and that means current process, but I guess here we have to do get PID. And get PID is in uni-std. Get PID. Okay, here we go. Yeah, and I think we can just compile it and see what's happening. All the extra GGDB and test C. Okay, and yeah, it worked. So now what I want to do is I will break basically on my handler, right? And I'm going to check what's happening after, what is on the stack and what's happening afterwards. So, and what will be on the stack, by the way, we should find the uContext structure there. So we might take a look. GDB out, break on my handler, run, okay. Signal received, continue. We need to continue. We can actually, so it's like this. If a signal is being sent to the debugger, then the signal is sent to a process which is being debugged, then the debugger gets information about it first before the process is able to process it. I guess we chatted about that on the debugger live streams, where we were trying to write a debugger for or debugging loop actually for Windows and for Linux. In any case, so that's why I had to continue here, because the debugger got its hands on the signal. It's quite easy to set it to ignore the sighub. Anyway, and then we are, where are we? Let's do display 10i rip and set this as assembly flavor. Anyway. So this is the handler, and I'm actually curious what is on the stack at the beginning of the function, so now, and then what is basically going to happen after we execute this instruction. Where are we going to return? So let's try by testing what is on the stack. This is 0. This is pretty weird. Did it execute? Yeah, probably because I set the handler here, it already executed some instruction. So this was my handler. Yeah, it already went through this. So okay, let's do 10 instead. GX is, by the way, for giant. Giant means 64-bit. X means hexadecimal. So here we go, and either this or this is the return address. So let's see what is on the return address, under the return address. And let's do 10i and this address. Wait, without this. I have no idea what's this. So this might not be the return address. I'm too lazy to actually calculate it. Yeah, okay, here we are. And here we have some restore RT and something syscall number 15. So let's check what's syscall number 15, but that's probably going to be Sigreturn. x86-64 syscalls. And yeah, the usual list, which usually requires this. Perfect. Now, 15 Sigreturn. Here we go. What's the difference between... Are there like different versions of Sigreturn? No, there's just this. Perfect. And it takes an unused argument. Why is it even noted here that it takes an unused argument? Well, okay. So basically when we return to this, it will... And I guess you can see that there is like no return here because the Sigreturn is supposed also to read the new value for the instruction pointer register, because it's again is like reads the whole context. We'll see. I guess we can see now what is in the context, or can we? Well, we might be able to do that in a second. So let's look here. So that means that if this was the return address, right? So this from here, starting from here, should be the context. And so this is the address. Let's try to print it. Wait, u context t, okay, pointer. This is the address. And yeah, now I think we need some pretty printing here. How did you pretty print? There was some way to enable it in GDB. Yeah, pretty. Set print pretty on. Okay, this is what I was looking for. Let's try again. Yeah, this is much more readable. And let's continue without paging. So let's see if this makes any kind of sense at all. Let's see. Some flags at the beginning, then the stack, which totally SP. Yeah, but this doesn't make sense. I'm not sure we actually hit the proper... Oh, the flags might actually tell us what exactly is in this context. So we need to... Let me open another terminal. We can check exactly what can be in that structure, because the uContext structure is pretty large and not all of it can be filled. It's like same like on Windows. It usually has some flags telling you which exactly fields are filled and which are not filled. So to do that, we need to go to our grep uContext t user include, and we're looking for the definition of the structure. I will, by the way, go to the questions which you might have in a second. And here is the file which we need to read. Okay. Okay, now flag. Let's just look for flag. That didn't help at all. Yeah. But where are the values of the UC flags? Okay, instead of doing it here, I'm just going to, I guess, like, Google it. Here, here, and here. UC flags, UC flags. What's the UC flags? Okay, so it's UC underscore something. So let's look for UC underscore, no. Let's go and grab for, where is it? In which files is it? So UC underscore something, and yeah, this is going to fail hard, but let's try. Yeah, let's look for FP. Okay, that's better. It's in a different file of the same name in the ASM directory. Okay. So we have 7 there, right? So that means is extended state information, and then sig context, which I guess, and strict restore, which doesn't tell us too much. But I guess if we would read it, we would know that some, which, okay, I think we might have to read it. Oh, that's interesting. Yeah. In all honesty, I don't think there is anything super much important. I did think it would contain which exact registers are there, but it doesn't seem to contain it. So yeah, let's ignore the stack anyway. Sorry. And let's look what else. Here are the general purpose registers, which would be probably, I don't know, well, I don't know what the order is, and we will have to probably check it out. That's probably like RAX, RBX, RCX, RDX, and so on. Then floating point registers. Oh, I'm not really sure what this is because it's only one value and there are a lot of floating point registers. Is this like a pointer to where the floating point registers are? It might be like that. And then some signal mask information and some other registers. Yeah, I think it looks somewhat fine, though I would love actually GDB to show me this in, you know, in actually like hexadecimal, because it's quite funny. At the beginning, when folks like learn hexadecimal, they're like, why are these folks using hexadecimal? It's like way better to use decimal. And now I'm like, yeah, like, why is this decimal? Can folks use hexadecimal? Okay, this looks pretty legit. What we might want to do is we might want to kill like the function, and it's just like puts this value in AEX and then does the syscall. So this is actually the place where I would expect it to go into the jump into the signal handler. So actually in EIX, I would expect this value. So how much is it? It's like 62. So we can check here if the 62 value is here. It's not here, so I'm kind of worried that something is wrong with this context, but I don't think that really matters, in all honesty. What we can do is we can actually like do just step forward through this handler. I'm going to call finish, and it goes to the restore. Finish goes to the last to the next instruction after the return of a function. And yeah, and now we are going to restore probably it and single step, and let's see what happens. It might actually just continue execution, but no, it goes to kill. So let's look at the register values. We had, did we hit any any values here? Yeah, like R9 had this value. Then R8 had this value. So we were, I think we were off by something in the structure, but we were actually in the proper structure. RCX had this value, it was 9495. Did we see this value somewhere in the structure? 9495, yeah, it's here. So we were like pretty close to the actual context which got restored by this opcode, and now we can just, you know, continue execution from here, from the signal handler, and it will just, yeah, exit normally. So I guess how it works, how the syscall works is pretty clear. Again, it's being called automatically when the signal handler leaves. Our signal handler leaves, it goes to the restore RT well, function, which actually calls the Sigreturn syscall, which does takes the structure, this uContext structure from the stack, and then it loads it into the registers, like these registers, and continues execution from wherever the rip is actually pointed to. So that's all we need to know about how it works, and now we need to check how to apply it to an exploitation scenario. And from what I'm reading here, it's actually like this: is we will have, it's pretty useful in situations where you have only, you have like a large buffer, and at the end of that buffer there is the return address which you overwrite, and you can overwrite only that and probably nothing else after that, so you cannot really do a proper return-oriented programming without doing some kind of a pivot, for example. But if you return to this gadget here, yeah, to this gadget, then it will actually take the values from the buffer, which you can pre-fill with whatever values, and load them into the context and continue execution from there. So this is like basically a perfect pivot, which allows you both to like switch the stack to another place. Well, I'm not sure really about the stack in this case, but because like the stack part wasn't filled. But let's assume that's also the case. Can we actually, I don't think, wait. So this was the stack value DA, okay, and then when we listed the registers, it was RSP. EOB8. EOB8. What? No, that looks fine. So by fine, I mean it actually doesn't seem to change the stack pointer, which isn't great. What's this value? 7320. So if we look here at the structure, is this value somewhere here? 7320. It's here. So yeah, so maybe it actually, we are actually able to do the stack pivot as well. So, you know, so take the buffer, for example, and make it our new stack, like just shift the stack a little. So that would enable to load more gadgets, but and execute more gadgets in return-oriented programming. But what is more important is that it allows us to set all these different registers to the proper values they're supposed to have. And that actually might help a lot. Now, yeah, I think like this is actually, if we control some memory on a known location and we know where the gadget is, and I'm going to disable ASLR for the sake of for the sake of this exercise, because let's assume that we somehow bypass the ASLR anyway. That's a fair assumption to make. ASLR is usually easy to bypass. So yeah, I'm going to disable that, and probably with that we can do execute a shell just using one gadget, like the Sigreturn gadget. So this is a really good and really strong gadget, and I hope we'll be able to do that. Cool. So let me look at the questions really quick, and there are only 4 questions from you. So let me take a look, and then we will write the example program and try to exploit it. Okay. Show. You will see the questions here. Again, if you have any questions, then do write to KrzaQ, whose nickname is here. Yeah. Who cares? When will be the next stream? So if you speak Polish, then the next stream is going to be tomorrow. If you do not speak Polish, then I'm not sure about next week's live stream, because it hits like a day off, and I might not be around, but in 2 weeks there should be one. Like either next week or in 2 weeks. Can you please explain a bit more about the signal frame, like all the stuff that is not regular register? That's a good question. Can I? No, I cannot explain it because I do not know the details. This is an excellent question, a non-standard model by the way, but I just do not know. So instead of me looking at the manual and reading it and then telling you what basically is written in the manual, I think it would be just faster for you to look at the manual. I'm not super experienced with Linux exception handling. I'm more versed on like how it worked on Windows, and not even the newest Windows, but like the Windows some time ago. Yeah, I need to catch up. Like, that's what happens if you do not like, you know, continue with everything when you have all the information. Christian, why does Gunveil still uses PHP in web development? I was suggesting if he can teach us how to develop a PHP website with all possible security to mitigate known attacks. So I both use it and I don't use it. As in, what? Okay, anyway, I use it as in, I use it for prototyping, and I do not use it for anything serious, which means that my blog, which is in PHP, is actually a prototype, but and so is the paged out page. Then that being said, if you're looking at my websites and you see .php, that might also mean I'm trolling you, and that part is not in PHP, because I like to do that. Like, even my Python stuff might have .php extension. Can I teach you how to develop a website with all the possible security mitigations to known attacks in PHP? That's not a bad idea actually for a topic. So let me just note it. Okay. Dohan asks why not Sig user 1 as docs internet. I don't know why. Like if Dohan is, I think, asking about why is Sig hub used for config reloading instead of Sig user 1. I don't know. I have no idea. It's a good question. Dashin writes, I really like the cover of Paged Out Institute Paged Out. It looks really awesome. Yeah, it looks really awesome. Like the artists which we hired for make the covers are quite amazing, like really amazing. And we are still waiting for a couple more covers to come. We already have covers for two issues, and we'll basically, like, as soon as the issue is out, we will put the cover art in full resolution online as well. So if you want to, I don't know, put it on your wallpaper or whatever. Will there be your article in the first issue of Paged Out? I hope so, and I hope that more than one, but let's see. Currently I didn't write one even because I'm still reviewing, but probably. Why do you use plain GDB instead of something like DBG? Depends actually on my computer. I have on some computers like set up on DBG, and on others I don't, and I just use plain GDB. So yeah, but depends. PwnDBG is quite cool, but it likes to throw a lot of errors on my screen, so that's why I'm not really using it on live streams, because I do not prefer no errors would be visible apart from the ones which I make. And I guess I make a lot of them. Okay, so this isn't required anymore, and now let's make something which we can exploit. So broken.c, let's code like this. I'm wondering, let's disable buffering. It's not really needed, but set buff, was it? Yeah, set buff, and then we should do buff null. Yeah, that should be fine. So let's disable buffering for standard input and to null, standard output and standard output zeros. This is just to get rid of some potential bugs which we might have while exploiting this. Yeah. Then let's call function ASDF. and the function is going to say hi, hello, and is going to create a large buffer where the buffer is going to be one. Yeah, just to make some space on the stack for us. I don't think it's going to be needed though. Well, whatever. Let's keep it as is. And then we are going to prefill the buffer so it's not optimized out. Let me think how to do it properly. Yeah, okay, let's do one more function, which is like, I don't know, calc. Okay, and this takes like char pointer, ASDF, and this does something like calculate some checksum. This is basically just so the compiler doesn't really do anything with my buffer. Size t, then length I++, and we do. Let's do unsigned here and unsigned here. And let's do, I don't know, some. This doesn't even have to be a proper checksum. So A, and let's do this with an ASDF I shifted by I, which is 32. That looks, that's a totally non-proper checksum, but let's leave it. And here we will do two things. We will read enough data into the A buffer from the. I'm going to like break this in a second from standard input. I guess we can do like roots high here just to be sure everything works from standard input, and then we are going to call the calc and like printf the hash. So okay, calc A and then size of A. Okay, something like this. And I'm not going to optimize it anyway, but GCC broken GGTB, because we will want to debug it probably. And now broken, let's go broken. Let's do dash wall dash extra. Okay, what? Why? Oh, because this is not C++, right? Okay. Yeah, and then C++ that would just, you know, initialize it with zeros, but this is not C++, so let's see if it works. And, no, that's broken. Now it waits for 1024 characters, so, okay, I have to feed it 1000 characters, perfect. Okay, and we have 1024, so let's fill it. And it gives us something which is... does it actually work? Oh, it does work, but there is the... Yeah, it goes enough times to cancel out the value, and it goes back to this value. Okay, that's fine. If I would do 31 here, it would probably be a little better. But it doesn't have to be a proper hash. I don't know why I'm optimizing this hash if it doesn't have to be a proper hash. Okay, that's fine. That's just an accident that it reverted to the original value. Okay, KrzaQ says that this initializes like it with zeros, and this, I think, from newer versions of C also would work, but I don't need to have it initialized anyway, so that's fine. Okay, so now I have this, now I need to break it, so I'm going to break it by, let's do gdb brokens. I need at least a config which says that this assembly flavor to Intel and this as ASDF. What I want to know is how much space did it actually reserve for the return value. And as you can see, our buffer is so our buffer was 1024, right? But hexadecimally that is 400. So it actually added 10 to it, so 410, and then we have this push, so it's like 18 hexadecimal on top of it. Which means if I will read plus 20 hexadecimal or 32, normally I should override the return address as well. So let's try to do that, and let's see if it actually crashes. I need to recompile though, and I need to run, and I need to add multiple A's. So okay, 1, 2, 3, and this is where we should hit the return address. I'm going to put C here, and I'm actually going to run it under GDB. So run, yeah, and copy this. And stack smashing detected. I think I have to disable it because I just overrode the cookie, and we cannot have a cookie for this exercise. Or we can leak the cookie. So yeah, we cannot do that. By the way, as you can see, they actually fixed one of the tricks to, well, that you could use while exploiting the stack smashing detection mechanism, which was you basically here what was here usually was the name of a binary which you run, but it was taken from argv, and argv is on the stack. So if you overflowed the buffer long enough, the buffer of a main thread, to reach the argv and overwritten it with an address of somewhere else where the cookie is, for example, then it would happily print out the cookie here, and if this got redirected to like the socket, for example, the attacker would get the cookie. And in some cases, or the cookie or some secret in memory or whatever, in some cases that actually might even be like useful, because, you know, the cookie changes with each execution. But if the process is, for example, a fork of another process, like in a fork server, then that cookie value is same for all the children of that fork, which do not run execve, just, you know, standard fork without execve. In any case, so yeah, now Ubuntu actually says unknown because it doesn't use the argv value, which is great, which is amazing that they fixed it. And there are some more details here. This actually is printed not to standard output, this is printed to the terminal, unless there is an environment variable to tell it to print to standard error output. And guess where there are by default the environment variables? Oh, on the stack. So yeah, the attacker could just like override it with, like, override the environment variables to add this, so it would be printed out to standard error, and that might actually be redirected to sockets depending on the exploitation scenario. But it's a pretty useful trick to know. Anyway, so that still means we have to disable the cookies, and I never remember how to disable the cookies. So gcc disable cookies, because we are not playing with cookies and ASLR today. Yeah, fno stack detector. So let's do this. Okay, now I'm going to disable ASLR in a second, by the way. GDB, by the way, disables ASLR anyway, but we want to connect to this probably with some networks socket anyway. Okay, execve, perfect. Now IR rip is, we didn't hit it. Why didn't we hit it? Because it probably, no, well, let's see what's here. Oh, it called probably libc. So yeah, I don't want to exactly play with libc today. That means it probably filled, yeah, RBP with this, but RSP is still fine. IR, sorry. Yeah, we are probably, why did it fail? Where did it fail? It failed on, no, I think it's everything is fine, because it failed on return, but it didn't read the value, this value, which means we are off by something. That's probably because of a cookie. We are off by 16 here. Yeah, that should be fine. That's because the address is non-canonical. Let's just restart it. I'm going to explain it in a second. And oh yeah, and it's still reading, so wait, let me fix that. Here, it's reading too much. Let's recompile it. Okay, IR. Yeah, we are at red. That's perfect. So on 32 bits, it would just like fill the EIP on 32 bits with a value, and then it would crash when it would try jumping into 41414141, or like 4C, 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 4C in our case. Let's see if that's actually the case, by the way. 1GX RSP. Yeah, we are. This is like CCCCCC, so we are hitting the proper value. But because on 64 bits, the addresses need to be in the canonical form, where the top bits are like, I don't remember, top 12 bits or top something bits. Whatever is the, sorry, I cannot into math. 64 minus, yes, top 16 bits are supposed to be either all ones or all zeros. If they are all ones, that means that the address is in kernel mode. If they are all zeros, it's in user mode. And like this address obviously doesn't have, like, the top values are obviously not zeros, they are like something else. So that's why red, while it tries to load the non-canonical address into the the RIP, the instruction pointer, it crashes because it cannot, because it's not a canonical address, therefore it crashes. If we would fix it, then it would just work properly. But what I'm going after is that it actually works as intended, so that's fine. And now what we need to do is we need to disable ASLR, and I'm actually going to disable ASLR system-wide. So disable ASLR, which you shouldn't do on production, and you should remember to, you know, just... There are ways, by the way, to disable it for one process, but I mean, we are just playing with it right now. So let's do this, and I'm going to actually turn off the microphone. Okay, so yeah, now it is disabled, which means that we always should get the same value, the same addresses. And I'm quite curious what the addresses are, but before we get there, I want to do one more thing. I want to do here... Wait, no, I don't have to. I was going to propose, like, doing a break, adding another fread or like get char or whatever stops the execution until I can attach a debugger, but that's not really needed. Perfect, which means I need to do, I need to just run it through a network, and to do that I'm going to use NC. Which NCs do I have? I have it both, and I don't remember which one is which. Traditional. I want -E, yeah, it's here. It's dangerous, don't do it at home, yeah. So, traditional -L -V -L -P, and P is going to be the port, which is 4444-E and broken. Okay, so now it's supposed to run the server, and I need, what do I need? I need my other, here we go, console. Let's try to connect to it. So, and C-V no. Okay, yeah, we connected and it says hi, so now we need this thing. Boom, and it crashed, core dumped. And it's actually lying. I'm pretty sure there is no core here because it has, kernel doesn't want to dump cores on some file systems, for example, shared file systems from the VirtualBox. So I would have to execute it in a different directory to actually get a core dump. But I don't think I need it. What I need to do is I need another, yeah, I need another terminal to be able to debug it. I don't think I will use the debugger too much, in all honesty. So let's assume I'm not going to use it too much. I need to connect. And after connecting, I need to do ps, or like pgrep broken. And this is, and what I really need is I need the map. Yeah, that's basically it. So cat proc maps, and I would like to like maps.txt, just write it somewhere here. This is the map, the process map which we get, sorry, the memory map, and I'm going to not wrap it, wait, I don't want to wrap it, yeah. And these are the addresses which we are going to use. Well, the addresses which are really interesting for us, I think, are these ones, which is the libc, because in the libc there is the Sigreturn gadget which we need to find. So we need to find that gadget in libc. And to do that, I'm just going to copy this file here and put it in some disassembler of choice. I'm going to use IDA today. Though, yeah, because it's just easier to run it with a given file. Otherwise I would use probably Gidra or Gidra, however you call it. Okay, and we know it was called restore something, restore RT. Is it still processing? Okay. If it's still processing, then give me 10 seconds. I need to grab water. Right, I actually have it here. Perfect. So let's see if we can find restore. It's not here. Is it in some other place? Where is it actually? We didn't check it last time. Let's check it now. GDB out break on handler. This is the previous example I've written, right? No, break my handler. Okay. Oops. That was an EEPROM chip, which you just heard probably falling down. Thankfully, it's in a box, and it has a habit of falling down from my desk. Anyway, okay, it's broken. Now we run it. We continue, and we finish. And where are we? Where are we? Wait, it finished too fast. Let's run again. Continue. Okay. Let's just break on like here. Continue, and let's single step. Oh, where does it return? Why does it return already? It's probably like some GDB magic. Okay. Well, let's do it the other way we did it last time. And this. What I'm trying to determine is where is this located. Is this in libc? Because this is again the yeah, this is the restore RT. Where is it located in? So I need info proc mappings. Okay, this is totally not readable. Okay, and the address is 7E02 100. 7D7E, this will be this. So no, it's somewhere in libc. Yeah, it is somewhere in libc. Let's do something like this. In IDA, let's do edit segments and rebase program, and let's put this image, like the glibc in IDA, let's put it on the same address. And now let's try to jump to this address and see if it's there. And yeah, it is here. It's just not, yeah, I don't know why. It's not in the function list, but as you can see, it is here. So we know that we have to return to this address, basically. Okay, so we can start writing the exploit, and I will use my... You probably want to use like whatever pawn tools or yeah, whatever framework for exploits. But as if you're watching my streams, you know I have my own really bad code base for writing exploits, which is called Pwnbase, and Pwnbase is... It barely works, but I know it really well, and there's almost nothing here in all honesty. So yeah. Here I need to put where to connect, and then it connects, and here I just put my code here. So I need to read hi message, right? Because when I connect to somewhere, it displays hi. Hi, so I need to read that. So print receive until I get the hi message with end of the line. Then I need to send my exploit, so send all my exploit, and then it will just go into interactive mode, which is great if we get a shell. Otherwise it will just act as it will receive data until it finishes. Now, okay, now exploit, I need to actually define it. So at this moment, what I'm going to do is I'm going to actually see how many A's do I have here. I should have, okay, 1,000, what's a weird number? But okay, no, that's fine. So 1032, so A times 1022, and to that we are going to add, well, it's CCC here, but we actually know where we want to jump. We want to jump here, right? Into this address. So one of the functions which I have here is actually something called DQ, where I can put the value, and it will convert the value into a little endian 64-bit integer. Yeah, it's like, it's just this, there's no magic here. It uses the standard struct pack interface for Q, which Q stands for quad word being 64-bit. And there's this little thing here says it's little endian, like the triangle bracket, right? Or less sign, whatever you want to call it. Okay, and now we can actually run it. So we are not going to use this. Okay, let's. I'm trying to determine what is which, where I have what. Oh, let's put it like this. And okay, so running this, now I need to connect to it, but after connecting to it, I would love to have a GDB. So no, and what I'm going to do is I'm going to not copy broken, I'm going to do pwd, and I'm going to go to temp, and I'm going to create so 77, and I'm going to do ulimit-c unlimited to have the core dump when it crashes. So I will not have to attach the debugger, I will just look at the core dump of what happened and what are the state of registers. And yeah, and I just run it, but not like this, I run it like this. Okay, so it's running now, and here I'm going to run my Pwnbase. And it connected and it crashed, and we have a core dump, and we can do GDB this with the core. Here we go, IR. Okay, so it totally failed, and that's not great. Okay, and it's something weird is going on. The core file isn't super small, but GDB has some problems with it. Yeah, something. Do I really have to attach the debugger? Okay, I'm going to have to attach the debugger. Well, seems it's not really. I cannot do anything about it, so let's attach the debugger. And to attach the debugger, I will have to modify my exploit, but after connecting, it actually pauses for a second, and like, so here, let's see here. Let's do this and run. This is Python 2, so raw input should stop the execution for some time. but gives me a moment to attach the debugger actually. Okay. Which means what? I will have to sudo to attach the debugger, right? Because this is a yeah, this is a new Ubuntu, which means that it has on new Ubuntu you basically cannot attach a debugger to another process unless you're root. You can start a new process under a debugger, but you cannot attach it. Okay, it's running. Then that means here I'm going to do this. Thankfully, I do not have any timeouts, which means it will not disconnect. If I don't do anything right now, it will not disconnect, which is a good thing from where I'm standing. And here what I need to do is pgrep broken. This is it. And here I need to do gdb pid and this pid. Yeah, operation not permitted, as I said, so I need to do sudo and okay, here we go. So we can continue and we can press enter and segmentation fault. Let's look at the registers. The registers are totally do not have any values as expected. Now this is something I somewhat expected because all the addresses, there are addresses which will be read into this and they're in a non-canonical form, which means, yeah, it will not really, we'll have to use some time to properly create the buffer. It will not read to probably format the buffer, right? As we saw, there are some flags in the context and so on, so we will have to deal with that, but that's fine. What we have to do here is, what I'm wondering about is where are we? So we are at, oh, this is not going to work at all. What's RSP value then? RSP, wow, it actually like zeroed all these, so that's quite funny. But not unexpected. Now, one thing which I'm wondering about is if I didn't mix up on what side do I have to put the, you know, if I'm jumping here, right, then on what side of this is the, yeah, I know what mistake I'm making. The problem is that even when I'm hitting the cigarette here at this place, the Sigreturn, actually the register values aren't before it, they're after it. So that means I need to modify my broken a little bit, just a little bit. Here we go, let's do, yeah, this is the space I wanted to make. And okay, I think it's going to be afterwards, right? Or is it? Yeah, it might. I'm actually confused. We'll determine it one way or the other actually. But I think we did check it before, and yeah, it's supposed to be. I'm wondering, you know, if we have a return address here, then whether the struct, the U context should be here or should be here, but it cannot be here. There are multiple reasons for it not to be here. It should be here. Okay, but that means that I have to add some stuff. I don't think the compiler would remove this, but let's just keep it, especially without optimizing it. So, okay, we can do this, we can break here. Can we break here? Oh, we cannot break here because we are still in the debugger. So let's exit the debugger, and now let's do GCC. Yeah. Let's run it again, and here what I'm going to do, this isn't needed anymore. This isn't needed, or is it? This isn't needed either, so let me close it. Here broken might be needed, and here, okay, then let's do I'm actually going to do something fun here. I'm going to overwrite it with 7s. And I'm going to put the 7, how many times? We have a buffer of, so 128 times should be fine. Oh wait, one more thing, here. I need to increase this to, yeah, let's do it like this. And again, I need to recompile it, restart it. So I have, you know, I read enough of data. So that means I have to do 1024 here by 8, because 8 is the size of a word I'm putting there. And let's try to run it again. Okay, attach, continue, and execve. Okay, this is, yeah, okay. This is perfect. This is exactly what we wanted. Well, not really. We will have to put proper values everywhere, but because, for example, rax is 0, but we don't care about rax, in all honesty. We care about RSI, RDI, probably these, and probably these. And obviously like these ones, because we also have to put the stack somewhere in a place where we know it will work correctly. Because ASLR is actually turned off, I'm going to use the values. But I need first to determine what is where. And to do that, I'm going to actually do something else. I'm going to create an array of values. And actually there's a function for that in Python. Hey, did you know that? And how many values? 100 by 8. Okay. And now here, what I'm going to do is I'm going to do a join on x for x in that tab, Okay, let's see if this works, because I've chosen 7 because it's somewhat of a magical value for the U context as we saw before, but since I now broken it, it might be a little, it might not work like that. But this way, because this will contain values like 0, 1, 2, 3, and so on, I will know by looking at the registers at which, if it works, in which index is what value. And then I can change the tab under a certain index to modify a registry value, and that should help me a lot. Okay, broken, because I do not need to do anything with it. This, continue here, do this here, IR, perfect. Now we can see all the different values here. And we know that, for example, yeah, I wouldn't read too much into the 0 here, but for example, you know what, I'm just going to copy this, because this will be pretty useful to have somewhere handy somewhere, wait. Okay. And where am I going to put it? Wait, not here. Map. Yeah. I'm going to just create a new file called regs.txt, which contains these. And that means that, for example, if I want to modify rbx, then I modify tab under index 16. So let's experiment with that. So tab index 16, and I want to put here like because I'm putting a value here, right? So let's put one. Okay, this isn't an address, this is just a value. It doesn't have to have a canonical form, so that's fine. We can quit here, we can restart everything. Did I save this? Let's make sure I did save it. And let's rerun the exploit. And connect the debugger, continue, run this, IR, and yeah, as you can see, RBX is the value which I wanted it. So yeah, basically we control the values, which is pretty cool already. Now, what I'm a little bit afraid is this is totally broken, and I mean totally, because like we need proper segment values here, basically. These are the only 2 segments which are important-ish. All the other are like set to flat mode anyway, or like controlled by some different mechanism. We might have to restore either one of these two. So you know what? I'm going to run. Wait, I'm going to quit here. And I'm not really sure about the values here, like 17 and 3, because this might just not be true, because it's complicated, but the way it's loaded into it actually like does some verification. It might not load proper values, so this might not be 17. It might be something else. We will have to determine it at some point, but it might be 17, because like our IP is 15 and this is 17. I think the like last 3 digits, bits of that, actually last 2, tell about the mode which we are in, and we are in mode, well, 3, right? User mode 3. So this might be 16, it might be 14 as well, for all I know. So we will have to determine that in a second. But before we do that, I'm going to run this, layout, break on my handler, run it. And now I'm going to read the register states. So these are the proper segments, which I will have to put there as well. Because if I don't put the proper segments there, I cannot use the stack and I cannot use the... yeah, I cannot use, like, execute code. If CS is broken, I cannot execute code, basically. And I do want to execute code. So this is one thing. Then I guess I'm going to change this as well, e-flags, and I will have to have RSP fixed as well. I don't care about other registers, but RSP is going to be pretty important. And again, if you have ASLR, then first step you have to do anyway is bypass the ASLR, so this would bring us to this point. And then looking here, yeah, I believe this is free. I totally believe this is free. Because like it might be 4 as well, but I don't think so. So let's put 3. So tab 3 is equal to 2b. And this is a proper value. Then we can try the 17. I'm pretty sure it's not going to be 17, but we can try 17. Wait, is that... yeah, it's hexadecimal, so that's actually... yeah, I'm going to use hexadecimal. And here, 3. If you're not sure about what are these segments, how do they work, and so on, then yeah, I'm not going to discuss it here today, but it's a super interesting topic, actually. And there were really cool bugs in, like, really cool vulnerabilities in how the segments are handled by the operating system. So this is a really interesting topic. Okay, then we can try if it actually worked. Then run it here and attach the debugger. Continue, IR. Okay, we actually hit the proper ones. I'm quite surprised. So this is fine, then this isn't fine. IF is for like interrupt flags. How does it even... why are we even able to change that flag? Should be like only kernel mode should be able to change it. And in any case, I'm wondering where e-flags is in the U context. So I believe we actually started looking for the U context somewhere. E-flags. No, this is not the proper flags. Oh, EFL, and it's defined. Okay, so it's after RIP. So if we know where RIP is, then the e-flags is the next one, and RIP is 15, which means 16 is actually. Oh, we can see 16 here. Is actually where the f-flags register is, so let's change it to 16. We want to put, what do we want to put here? 206. And then we want to basically change 14, which is RSP. Yeah, we want to put the stack somewhere. We honestly don't care where it is, as long as it's in like a sane spot. And I don't know. Can I just like proc info mapping, info proc mapping. Sorry, info proc mappings. Yeah, the stack is here, so basically like anything close to it should be fine. So tab, oh, sorry, what was the ESP again? Sorry, RSP 14. 14 is going to be, this is the end of a stack, so we need to go a little backward, and let's go to F. So this kinda will fall into environment variables, and it will start overwriting environment variables. That's fine. We can overwrite environment variables, I don't mind. And the next important piece, which is the 15, RIP, this is going to be a little more fun, but we will get to that in a second. So let's put zeros and for one for the time being. Doesn't matter how many zeros. And let's break here. Let's restart it. Restart, then run the exploit. Here, continue. Yeah, we have a proper value in RIP, as you can see. So this is like Ender's Game. We are basically like just, we'll have to, well, we want to spawn a shell, so we control all the registers, as you can see, including the flag registers. I don't think any other gadget actually gives you this much control. This is, I realize this is like my new favorite gadget, apart from the magic gadget, which just gives you the shell, you jump there and it gives you the shell, right? This is my new favorite gadget. So by the way, I didn't say that, but I learned about this SROP when watching the pony racing. I think it was like the second episode or something like that. Pony racing, if you don't know, is basically like this live stream tournament where you have like 4 hackers usually, which are you see like the split screen of them trying to exploit something, and it's being commented by some awesome people. And so pony race or pony racing, was it? Yeah, this is the person, Zeta2, and was it pony racing? It was pony racing. My apologies. It was in episode 2, I believe. So if you look for pony racing, and yeah, they do a good job of commenting. You can take a look how it looks. I totally recommend it. Look for again pony racing, maybe with a space here. Okay, so to go back here, what we want to do now is we want to set up the registers in a proper way to be able to execute a shell. Now, how do we execute a shell? Well, I guess the easiest way to execute a shell would be to run system. And obviously I did close IDA. Why did I close IDA? I don't know. Yeah, and I want to go to system. And this is where I'm going to set my EIP2. So my EIP is going to be this address, which goes to system. And now system actually takes an argument, right? Which the argument, well, it's supposed to be, what do you want to execute? And as you can see, it goes into the RDI register, right? Like this is the first thing, system tests. And that means that we want to set RDI as well. And to set RDI, RDI, where are you? Here, it's OXD. So we have to set this OXD into like an address which points to string bash or sh. Thankfully in libc there are quite a lot of strings like that. So let's do shift 12 and looks for /sh and no, bin sh, perfect. And this string is, this is the address of the string. Because it's used by like system of all things, or like popen or some other stuff. So if we put this address here, it's actually like points to bin sh. And that's actually should be it if everything works accordingly, and it's not going to, because things are not so simple. I'm kind of sure we will have to like change some more registers for it to work, like RBP or something. But okay, let's see. So yeah, I'm just going to run it, see, and it crashes. So no, yeah, it's not so easy as I said. Let's do here. Sorry, too fast. Continue. Boom. Okay, but we are already in the system, which is good. And as you can see, system was called with bnsh, so that's also good. But it kind of like segmentation fault, and segmentation fault on this address. So let's see what is under this address. It failed here. So it jumped here and it immediately failed. And why did it immediately fail? So usually stuff like this happens when some pointer is... It's quite amazing that it failed so fast. I would expect like CS to be incorrect, so that it failed because CS is incorrect or something like that. But this actually looks fine. Let's run another... Yeah, let's run another console because I want to compare the values. Okay, these registers are like general purpose, it doesn't matter what's there. Then we have here, we have like the parity flag set and the IF flag, which is fine. Then we have, this is fine, and continue. And this is fine. So it crashes for some weird reason. And we have RSP set. And I don't think RSP is used yet. So this is pretty weird that it actually crashes. We might have some garbage values in some important register, which is not listed here. I don't know why does it crash. Yeah, like the problem is that like the reason why the CPU decided to produce a fault is one thing, but then it gets translated by the operating system into, like, for example, signals, as in Linux, which have much lower granularity, and because they need to be, you know, the same on each architecture, which means zigzag can be used in many different occasions, which are not really related to why it actually crashed. Okay, info. How do I display some other float? I don't think I've actually overwritten the float register. Info float. No. Yeah, I'm pretty happy with this, and again, this is basically we just jump there. It's not even as we jump here, we don't really jump here. It's like it fills the stuff and then like fills the register and then it suddenly crashes. I'm wondering if I have to do something interesting or magical here. So it's like it didn't call system. It just like jumped. It didn't even jump. I think my take on it is that it crashed in the middle of executing Sigreturn, which means it filled the registers with proper values, but it still executed in kernel mode and it didn't go back to user mode yet. Which is quite interesting. It might be related to something in the exception. Yeah, it might be related to the some other part of the U context structure, which I'm not filling. Let's see at the U at this structure. What do we have here? Okay, so it has like flags. There is a link to somewhere. Then there is the stack information, which is probably broken. Then there is the M context, the sigmask. This might be broken, and then there is the FP state, which is the floating point registers. And so you know what I'm going to do is I'm actually going to change my code a little bit. And in the exploit, instead of doing this, I'm going to do tab is equal to 0 multiplied by 128. And let's see now. So I'm zeroing instead of putting weird values everywhere, which weird values might be great for writing most of this code, but as you can see, they might actually like clubber a lot of stuff, and zeros will also clubber them, obviously, but 0 is a somewhat magical value, which somehow sometimes you can just squeeze it through. So that's fine. Let's do this. Let's run the exploit. This is not the exploit. This is the exploit. Perfect. Now let's attach the debugger. Let's continue, and let's continue. And now let's see, where does it? Okay, it's much better because as you can see, we are actually executing system. So we got further. So we are, so this is better. We are making progress, but it still crashes. Let's see, where exactly are we here? So one thing, oh, it actually is a return, which means it didn't execute correctly, but that's fine. You know what I'm going to do? I'm just going to do jump here. And yeah, I'm going to jump here and I'm going to see if I can just magic gadget it a little bit. But before I do that, let me still check where exactly did we go. Here. Okay, so we got here. Yeah, it's... I don't think it ever... Yeah, it never probably went here. So it probably failed somewhere before. And what that means is I'm actually going to change my debugging method a little bit. And instead of doing this, I'm going to actually do, let's run this, let's run the exploit. I'm going to do strace -p. Yeah. Okay, because this might actually tell us what was going on. So it went with clone and the clone, I think it worked. Then it went with wait, and then it got some signals. Yeah. Okay. You know what? I'm not going to bother with system after all. I'm going to just go for straight execve, because why not? So let's go with execve. System actually has quite a lot of dependencies. If you like, in exploits, it's pretty common. System doesn't work. We might be able to get it to work, but let's not spend time with that. Instead, let's go to here, which is calling execve. And I'm actually going to yeah, I'm actually going to jump here. This might be even a magic gadget. Then it will save us some time. If it's not, I'm pretty sure I can at least fix the environment enough for execve. So execve is actually supposed to work, even if everything is broken in the process, execve is still supposed to work. It's kind enough to do that, because it's a system call in the end, right? So let's do this, let's attach the S trace again, and let's continue. And we got execve, which is fine. And then it got, yeah, this is totally incorrect, which is fine, because we will fix it. Now, execve should get, let's do it like this. We are going to jump to this address. Okay, and now we are going to set all the proper register values, and we did already have the syscall table somewhere here, right? Yeah. So let's look at execve. We need to put the file name, the link to the arguments, and like to a table which contains pointers to arguments, and this can be null. So this register as RDX, we can put null in RDX, we can put probably null in RSA, and I'm pretty sure we cannot put null in RDI. So, okay. So RDX, we put null in RDX, but it already should be null. RDX is 11. Is 11, we put null. It might not work. Then in RSI, no, it will work. For RDX, for environment variables, it will work. For RSI, we, sorry, which one is it? E. I don't think 0 is going to work. I'm pretty sure we will have to do something magic here, but let's start by testing with this. Okay, let's do this, let's do this, let's attach strace. Let's do this, and yeah, it actually worked. So that's it. It's a pretty amazing gadget in the end, right? Because like you just change the values and you control all the registers. So I'm quite amazed actually by how easy is it to use this gadget. And in all honesty, I didn't count for setting the arguments to just null will work, but as you can see, it actually worked. So I could set both this and this to nulls, and then just point to the binsh string, which is in memory of libc, which I have to have the libc anyway to to use the Sigreturn gadget. So that worked well, and I guess that's it, right? We got a shell. It actually executed properly the. Yeah, it works. So that's it. Let's look if you have any questions. I'm going to put the code for this on my GitHub. If you're following my GitHub repositories, is going to be in this one, stream.en, and it's like github/gunveil. So yeah, and I will put it in the proper directory, which will be 077. And let's do questions now, if you have any questions. Again, if you have any questions, then do let KrzaQ know. His nickname is right here, because he is the person who actually looks at the chats and sorry. Okay. So, okay, Dohan writes, I meant your use of SIGHAP, not verse. If others make something weird, that doesn't mean you also need to. True, but I mean, this is just a test application, right? Which was supposed to check how signaling works. Any signal could have been used, so it didn't matter in this case at all. It could be sig user, it could be SIGHAP, it could be like almost anything else which just doesn't straight out kill your application or stop it. But yeah, if I would be, designing a new production application, then that's a really valid point. And well, SIGHAP is kind of standard, I guess, for reloading configs. But apart from that, I'm not sure I would use signals for that. In honesty, I would use some other RPC mechanism probably. Okay, in your pawn base, there is an error in line 48. Let's see, maybe I have like some old version there. 48. Oh yeah, this one. Yeah, I know. It's an old version probably. I'm pretty sure I have it fixed here. It's what the function is. Yeah, it's here. So I didn't upload the newest version probably, but you're right. This one it should be. This should be in. Yeah, sorry. Yeah, this should be in brackets. This is it. But I have it fixed in my version, which I usually use. In honesty, I do not. I put it here just for you folks to look at it, but I do not encourage you to use it. It's something I can use, but I would not make you suffer through using it. Just learn Pawn tools or whatever folks use nowadays. It's just I'm too lazy to learn Pawn tools. Have you tried using GDB extensions like Jeff, Beda, or Pawn DBG? Using vanilla GDB is really painful. Yeah, I did, and as I said before, I do have on some other of my computers, I do have Pawn DBG, for example, set up. So I do use it. I do not use it a lot, in all honesty, like a lot of functions, and I think I know vanilla GDB enough to do most of the things I need to do usually. Yeah, I do realize it would be probably faster if I would spend some time using like Pawn DBG and learning it by heart, but since I don't do too much exploitation nowadays, I never found a moment to do it. But it's a fair point. Maybe you should try playing Pony Racing. Any chance of that happening? Maybe, though, as I said, I'm not really exploiting too much stuff recently, so I would just fail miserably, probably. Okay, I guess that's it. There are no more questions, so thank you, folks, for being here today, and I really enjoyed learning about this technique. This exploitation technique is a really nice gadget. I mean, it's the next best thing after the magic gadget, or like one gadget, however you want to call it, exploit. So thank you to KrzaQ for being here and helping me with my streams. And again, I encourage you to look at the pagedout.institute to know if you can help out in any way. I really actually want the magazine to happen and to be successful, so if anyone wants to help us making that happen, then do let me know. And I think that's it. So thank you, everyone. I'm going to leave you with some music and see you tomorrow if you speak Polish, and either next week or in 2 weeks if you don't, on the next English stream. So that's it. Thank you. Bye bye. Have a great evening. Happy hacking, and see you next time.